Greetings to everyone. Today we are going to discuss about design of compression member. So here the given data is the load they will give. Okay. So for corresponding to that load, what is the section and whether the section is going to withstand that load and the connections. Okay, either bolt or weld, that we are going to discuss in this class. Okay, let us move on to the problem. So first of all, the given data. Design a strut carrying a factored load of 180 kilonewton. The length of the strut, is 3 meter. Design the end connection. So the here the given data are, they have mentioned the factor load P is equal to 180 kilonewton and the effect, the length of the strut L is equal to 3 meter and design end connections. Design end connection. Now let us move on to the solution. So end connections means we have to calculate that is the angle section we are going to prefer. Okay, so at the end we have to give the angle section, and here for the connection we should go for the bolted connection. Okay, bolted connection. So now what are the things we have to do means, first of all we have to choose a section based on area requirement. Okay, then after whether the section is safe to handle handle the given load. After that, have to go for connection design. So connection design means here bolted connection. So how many numbers of bolts requires, that we have to find out. So these are all the some common steps. Okay, let us move on to the solution part. So first, here the FCD value we have to assume ourselves. Okay, so for the angle section, okay, we mentioned that the end connection, so angle section, the FCD value we are going to take between 70 to 90. Okay, and maybe assumed as 135. Okay, 70 to 90 Newton per mm square mostly we have to choose, and at the maximum we have to go for 135 Newton per mm square. Not only for angle section, for angle section this value, and the remaining I section we can go like this. So now I am going to assume the FCD value is 90 Newton per mm square. So we know one formula, that is PD is equal to AE into FCD. Okay. So here we are going to assume that P is equal to PD is equal to 180 kilonewton. From that FCD we know that 180 is equal to 180 into 10 cube Newton. Okay. So FCD is equal to 90 Newton per mm square. Okay, so from this we have to calculate AE required. Okay, so AE required is nothing but P by FCD. So P value is nothing but 180 into 10 cube divided by 90. So how much? So 180 into 10 cube divided by 90. So it gives us a 2000 mm square. 2000 mm square. So this is the area required. So from this, based on this value, we have to go for selection of section. Selection of section. That is angle section from steel handbook. Okay. So whatever the area is more than 2000, that section we are going to either equal angle section or unequal angle section. So that is our wish. So that we have to choose right now. So from the handbook. So angle section we are going to choose. So just select the angle section. So here it is I section, here I, here channel, here angle. Okay, we can go for rolled steel unequal angle. Okay, so equal angle, rolled steel equal angle, rolled steel unequal angle, so that the section will be is not uniform in the lengthwise, breadth and height is not uniform. Okay, now based on that we are going to choose. So here the area is available. Okay, so based on this area we have to go for the section. So this section we can choose. Okay, so 150 by 115 by 10 mm, so that the area becomes 25.52. So 2552 mm square. Okay. Even we can choose this also. This is also high now. So 150 by 115 by 8 mm. That is also 2058. Okay. So let us try with this section. Okay. So select ISA 150 mm by 115 mm by 8 mm. So that area is equal to 2058 mm square. So the requirement is more than our provided. Okay. Sorry, the provided area is more than a requirement. Okay. Now let us move on to the conventional thing, such as design strength of the selected member. Okay. So we should move on to the next page. So design strength of the selected member. Design strength of the selected angle section. Okay. So PD is equal to AE into FCD. Okay. So now we have to, based on the sectional details, we have to arrive this PD. Okay. So our constraint, that is code book. Okay. So in the code book we can have this. So P should be less than PD. So P is nothing but our given load. Okay. So that value is lesser than design strength or not, that we have to check it. Okay. So our given load is 180 kilonewton. Then design strength of the member we have to calculate whatever the selected section. Okay. From that we have to calculate the PD value. For that FCD value we have to know what is the buckling class. Okay. So those things. So the buckling class will be arrived from this portion. Okay, from table 10. So for angle section the buckling class is with respect to C, okay? So that the alpha value we have to calculate, okay? And what is the end condition? They didn't mention any end condition, okay? So that we have to go for uh, one end fixed and another end is hinged condition we should go, okay? Now just for assuming, okay? So from table 10, the buckling class for angle section, the buckling class for angle section is equal to C, okay? Now assume assume one end fixed and other end hinged, okay? Okay, so so that effective length becomes 0.8 times of L. So 0.8 into 3 meters, 0.8 into 3. So it becomes 2.4. So we have to say for 2400 mm. Okay, effective length. Next PD, FCD value we have to calculate. Okay, so AE we know that slenderness ratio. Since table 9C, okay, will give the answer for FCD value, okay? So for that we need KL by R minimum, okay? So KL by R minimum is nothing but effective length divided by R minimum, okay? Least radius of gyration. So least radius of gyration we have to find out, okay? For the angle section. Um, So we have to find out Rxx value and Ryy value from the handbook. So from the handbook, Rxx value is 47.6, then here it is 34.1 mm Ryy. So that value now we have to take it. So Rxx is equal to 47.6 mm, Ryy is equal to 34.1 mm. Now KL by R minimum value, KL by R minimum is equal to R minimum is Ryy. Okay, so KL value 2400 divided by R minimum 34.1. R minimum is 34.1. So it becomes 70.38. 70.38. So now from table number 9C we have to calculate the FCD value. So we should go for the table number 9C. So table number 9C, okay, for the value of 70 and Fy. So Fy value we have to take it as a 250 Newton per mm square, okay, and corresponding to 70 the value is 152 Newton per mm square. So 70.38 I am going to consider as 70, okay. If it is 75 or nearer, then we have to go for interpolation. Okay, now. So now the value is very less, 0.38 only. That's why directly I'm going to take this value. Okay. So 152 is our FCD value from table 9C, of IS 800. The FCD value becomes 152 Newton per mm square. Okay. Now we have to go for design strength PD. So design strength PD is equal to AE into FCD. So AE value is 20. AE provided value is 2058. So 2058 is the AE provided, and the FCD value we calculated that 152 Newton per mm square. So 152 Newton per mm square. So by multiplying this 2058 into 152, it will give 312.8 kilonewton. So our P value, that is 180 kilonewton, is the given. Our member can withstand 312.8 kilonewton. So the condition is satisfied. Hence it's safe. Hence the section is safe to transfer load. So the second part is over. Okay. Here the first part I said choose the section based on the load. Okay. Second, whether the section is safe to handle the given load or not, that we have checked. Now we have to go for connection design. So connection design, we have to third one, connection design. Okay. So here this is our angle section. So I'm going to fix the bolt here. Okay. So how I'm going to, that is the number of bolt I have to calculate. Before that, I have to calculate strength of bolt. I have to calculate first. Okay. So strength of bolt is least of strength of bolt in shear and strength of bolt in bearing. So first I have to calculate these two things. Okay. Among them, which one is the least value? That value I have to go for number of bolts required. Then after, number of bolt required is equal to load on the structure divided by strength of bolt. Okay, so now first I have to calculate the strength of bolt in bearing and shear. So strength of bolt in shear. Okay, from page number 73 of IS 800 2007, VDSB is equal to VNSB by gamma MB. Whereas VNSB is equal to FU divided by FUB by root 3 into NN into ANB plus NS into ASB. Okay, here NN we have to take it as that is only one bolt we can have going to. Okay, now so NN is equal to 1 and the ANB is equal to 0.78 times of pi by 4 into d squared. So now we have to assume the dia of bolt also. Okay, so dia of the bolt we are going to assume as 20 mm. Assume dia of bolt is equal to 20 mm. Okay, therefore A and B is equal to pi by 4 into 20 squared. So 314.159 mm square. Sorry, into 0.78. So 245. So 245.044. 245.044 mm square. So this is the AMB value. And we all know that NS, that is number of shear failure in the shank, okay, now is equal to 0. So this term becomes 0. Okay, let us find out the value. And FUB, we all know that 400. Okay, FUB is equal to ultimate tensile strength of the bolt. Ultimate strength of the bolt, okay, is equal to 400 Newton per mm square. Therefore, VNSB becomes 400 divided by root 3 into 1 into 0, that is 245.044. So 400 into 245.044 divided by root 3. So 56.590 kilonewton VNSB. Therefore, VDSP, that is design strength of the bolt, becomes VNSB by gamma MB. So from table 5 of IS 800 2007, gamma MB becomes 1.25. Therefore, VDSB is equal to 56.59 divided by 1.25. So 45.272. 45.272 kilonewton is the value of VDSB. Okay. Next, in bearing, what is the strength that we have to find out? So, strength of bolt in bearing. Okay. So, VDPB is equal to VNBP by gamma MB, VNBP by gamma MB, whereas VNBP is equal to 2.5 into KB into D into T into FU. So first KB we have to calculate. So KB is the smaller of, so E divided by 3 into D naught. P divided by 3 into D naught minus 0.25. Then FU B by FU and 1. So among them, which one is least? That we have to check it. So FU, we know that. So edge distance, okay. So edge distance, we are going to take it as a 1.5 times of D naught, whereas D naught is equal to dia of hole, dia of bolt hole. So bolt dia plus clearance we have to add, okay. So bolt dia of bolt is 20 mm plus clearance is equal to 2 mm. So 22 mm is the dia of bolt, okay. So E becomes 1.5 times of D naught. So 1.5 times of D naught becomes 33 mm. Similarly, pitch P is equal to 2.5 times of D. So it is 50 mm. Okay. So substitute these values. So under FU, we know that 410 Newton per mm square. So now these values, E divided by 33 divided by 3 into D naught is equal to 22. Similarly, pitch, this value 33 divided by 3 into 22 becomes 0.5. Next, pitch, so 50 divided by 3 into D naught minus 0.25. So it becomes 0.5, sorry, 0.08, sorry, 0.508. So 50 divided by 3 into 22 minus 0.25 becomes 0.508. Next, FUB by FU. FUB is equal to 400, FU is equal to 410. So 400 divided by 410 becomes 0.976. 0.976, then 1. So among them, the least value is 0.5. Therefore, KB is equal to 0.5. Now, VNBP becomes, so 2.5 into KB is 0.5 into D, dia of bolt 20 mm, thickness of plate. So here the thickness of angle section is equal to 8 mm, okay, for the chosen section. Okay, 8 mm is the thickness of plate, or thickness of angle section. Next, FU or FUB. Okay, we are going to take it as 400 FUB, your bolt strength. Okay, therefore VNBB is equal to 2.5 into 0.5 into 20 into 8 into 400. So it becomes 80 kilonewton. 80 kilonewton. Therefore, VBBB is equal to VNBB divided by gamma MB. So gamma MB value is 1.5. So 80 divided by 1.25 becomes 64 kilonewton. 64 kilonewton. So strength of bolt in shear is equal to in bearing. So strength of bolt in shear is equal to 45.272. 45.272 kilonewton. In bearing is equal to 60 kilonewton. So among them, which one is least? In shear is the least. Therefore, strength of bolt is equal to 45.272 kilonewton. Therefore, the number of bolt required is equal to load divided by strength of bolt. So load 180 kilonewton, that is the total load on the acting on the structure, okay, divided by strength of bolt is 45.272 kilonewton. So 180 divided by 45.272, it becomes 3.975. So the value is 3.975. Say 4 numbers. Therefore, provide 4 numbers of 20 mm dia bolt. Okay, in the angle section. So if I'm going to have like this, so in the cross section I'm mentioning. So minimum pitch we have mentioned that 50 mm, okay, from this section. So based on that, so edge distance pitch both are similar, okay. So here the end distance is nothing but 33 mm, okay, balance each is 50 mm gauge distance and the pitch distance, okay. So we require 4 numbers of bolt 20 mm dia. So this is our final result. So this is the way we have to design the compression member. So first of all, we have to take care of these 3 things we have to do. One is, for the given load, we have to calculate the area requirement. So that is P is equal to AE into FCD. So FCD value we have to assume between 70 to 90 Newton per mm square if it is I section, okay. Sorry, if it is angle section. If it is I section, we can go up to 135 Newton per mm square, okay. So then after, we have to choose a section, either angle section or channel section or I section, that is based on our wish, okay, from the excuse me, from the handbook, okay, steel handbook. After that, that says that number whatever who selected, okay, now whether it is safe to carry the given load or not, that we have to check it. For that, we have to check P is equal, P should be less than PD, okay. So PD is nothing but AE into FCD. So FCD we have to calculate. For that we need KL by R minimum value, okay. Now based on the buckling class, we can select the, we can calculate the KL by R minimum value, okay. Then after, design of connection. So whether it is bolted connection, then we have to go for number of bolts required. If it is welded connection, then we have to go for length of weld. So this is the criteria we can have to design the compression member. Thank you.